In engineering and science, dimensional analysis is the analysis of the relationships between different physical quantities by identifying their fundamental dimensions and units of measure and tracking these dimensions as calculations or comparisons are performed. Converting from one dimensional unit to another is often somewhat complex. Dimensional analysis, or more specifically the factor label method, also known as the unit factor method, is a widely used technique for such conversions using the rules of algebra. The concept of physical dimension was introduced by Joseph Fourier in 1822. Physical quantities that are commensurable have the same dimension. If they have different dimensions, they are incommensurable. For example, it is meaningless to ask whether a kilogram is less, the same, or more than an hour. Any physically meaningful equation will have the same dimensions on the left and right sides, a property known as dimensional homogeneity. Checking this is a common application of dimensional analysis. Dimensional analysis is also routinely used as a check on the plausibility of derived equations and computations. It is generally used to categorize types of physical quantities and units based on their relationship to or dependence on other units, concrete numbers and base units. Many parameters and measurements in the physical sciences and engineering are expressed as a concrete number, a numerical quantity in a corresponding dimensional unit. Often a quantity is expressed in terms of several other quantities. For example, speed is a combination of length and time, e.g., 60 miles per hour or 1.4 kilometers per second. Compound relations with per are expressed with division, e.g., 60 miles, 1h. Other relations can involve multiplication, powers, or combinations thereof. A unit of measure that is in a conventionally chosen subset of a given system of units, where no unit in the set can be expressed in terms of the others, is known as a base unit. For example, units for length and time are normally chosen as base units. Units for volume, however, can be factored into the base units of length, thus being derived or compound units. Sometimes the names of units obscure that they are derived units. For example, an ampere is a unit of electric current, which is equivalent to electric charge per unit time and is measured in coulombs per second. So 1A equals 1 C per second. 1 Newton is 1 kilogram, meter per square second. Percentages and derivatives. Percentages are dimensionless quantities, since they are ratios of two quantities with the same dimensions. In other words, the percent sign can be read as 1/100th, since 1% equals 1/100th. Derivatives with respect to a quantity aid the dimensions of the variable on as differentiating with respect to on the denominator. Thus, position has the dimension L. Derivative of position with respect to time has dimension Lt-1 length from position, time from the derivative. The second derivative has dimension Lt-2. In economics, one distinguishes between stocks and flows. A stock has units of units, while a flow is a derivative of a stock, and has units of units, time. In some contexts, dimensional quantities are expressed as dimensionless quantities or percentages by omitting some dimensions. For example, debt-to-GDP ratios are generally expressed as percentages. Total debt outstanding divided by annual GDP, but one may argue that in comparing a stock to a flow, annual GDP should have dimensions of currency, time, and thus debt to GDP should have units of years, which indicates that debt to GDP is the number of years needed for a constant GDP to pay the debt. If all GDP is spent on the debt and the debt is otherwise unchanged. Conversion factor. In dimensional analysis, a ratio which converts one unit of measure into another without changing the quantity is called a conversion factor. For example, kPa and bar are both units of pressure, and 100 kilopascals equals 1 bar. The rules of algebra allow both sides of an equation to be divided by the same expression, so this is equivalent to 100 kilopascals, 1 bar equals 1. Since any quantity can be multiplied by 1 without changing it, the expression 100 kilopascals, 1 bar, can be used to convert from bars to kPa by multiplying it with the quantity to be converted, including units. For example, 5 bars times 100 kilopascals, 1 bar equals 500 kilopascals because 5 times 100 over 1 equals 500, and bar cancels out, so 5 bars equals 500 kilopascals. Dimensional homogeneity. The most basic rule of dimensional analysis is that of dimensional homogeneity. Only commensurable quantities may be compared, equated, added, or subtracted. However, the dimensions form a multiplicative group, and consequently, one may take ratios of incommensurable quantities, and multiply or divide them. For example, it makes no sense to ask whether 1 hour is more, the same, or less than 1 kilometer, as these have different dimensions, nor to add 1 hour to 1 kilometer. On the other hand, if an object travels 100 kilometers in 2 hours, one may divide these and conclude that the object's average speed was 50 kilometers per hour. The rule implies that in a physically meaningful expression only quantities of the same dimension can be added, subtracted, or compared. For example, if MMAN, MRAT and LMAN denote, respectively, the mass of some man, the mass of a rat and the length of that man, the dimensionally homogeneous expression MMAN plus MRAT is meaningful, but the heterogeneous expression MMAN plus LMAN is meaningless. However, MMAN, L2 man is fine. Thus, dimensional analysis may be used as a sanity check of physical equations. The two sides of any equation must be commensurable or have the same dimensions. Even when two physical quantities have identical dimensions, it may nevertheless be meaningless to compare or add them. For example, although torque and energy share the dimension L2mt-2, they are fundamentally different physical quantities. To compare, add, or subtract quantities with the same dimensions but expressed in different units, the standard procedure is first to convert them all to the same units. For example, to compare 32 meters with 35 yards, use 1 yard equals 0.9144 meters to convert 35 yards to 32.004 meters. A related principle is that any physical law that accurately describes the real world must be independent of the units used to measure the physical variables. For example, Newton's laws of motion must hold true whether distance is measured in miles or kilometers. This principle gives rise to the form that conversion factors must take between units that measure the same dimension, multiplication by a simple constant. It also ensures equivalence. For example, if two buildings are the same height in feet, then they must be the same height in meters. The factor label method for converting units. The factor label method is the sequential application of conversion factors expressed as fractions and arranged so that any dimensional unit, appearing in both the numerator and denominator of any of the fractions, can be cancelled out until only the desired set of dimensional units is obtained. For example, 10 miles per hour can be converted to meters per second by using a sequence of conversion factors as shown below. It can be seen that each conversion factor is equivalent to the value of 1. For example, starting with 1 mile equals 1609 meters and dividing both sides of the equation by 1 mile yields 1 mile. 1 mile equals 1609 meters, 1 mile, which when simplified yields 1 equals 1609 meters, 1 mile. So, when the units mile and hour are cancelled out and the arithmetic is done, 10 miles per hour converts to 4.47 meters per second. As a more complex example, The concentration of nitrogen oxides in the flue gas from an industrial furnace can be converted to a mass flow rate expressed in grams per hour of NOx by using the following information as shown below. NOx concentration equals 10 parts per million by volume equals 10 ppm V equals 10 volumes, 106 volumes. NOx molar mass equals 46 kilograms, kg/mol. Flow rate of flue gas equals 20 cubic meters per minute equals 20 cubic meters per minute. The flue gas exits the furnace at 0 degrees Celsius temperature and 101.325 kilopascals absolute pressure. The molar volume of a gas at 0 degrees Celsius temperature and 101.325 kilopascals is 22.414 cubic meters, kg/mol. After cancelling out any dimensional units that appear both in the numerators and denominators of the fractions in the above equation, the NOx concentration of 10 ppm V converts to mass flow rate of 24.63 grams per hour. Checking equations that involve dimensions. The factor label method can also be used on any mathematical equation to check whether or not the dimensional units on the left-hand side of the equation are the same as the dimensional units on the right-hand side of the equation. Having the same units on both sides of an equation does not guarantee that the equation is correct, but having different units on the two sides of an equation does guarantee that the equation is wrong. For example, check the universal gas law equation of PV equals nRT, when the pressure P is in pascals, the volume 5 is in cubic meters, the amount of substance N is in moles. The universal gas law constant R is 8.3145 pascals m cubed. The temperature T is in kelvins. As can be seen, when the dimensional units appearing in the numerator and denominator of the equation's right-hand side are cancelled out, both sides of the equation have the same dimensional units. Limitations. The factor label method can convert only unit quantities for which the units are in a linear relationship intersecting at 0. Most units fit this paradigm. An example for which it cannot be used is the conversion between degrees Celsius and kelvins. Between degrees Celsius and kelvins, there is a constant difference rather than a constant ratio, while between Celsius and Fahrenheit there is neither a constant difference nor a constant ratio. There is, however, an affine transform between them. For example, the freezing point of water is 0 degrees Celsius and 32 degrees Fahrenheit, and a 5 degrees Celsius change is the same as a 9 degrees Fahrenheit change. Thus, to convert from units of Fahrenheit to units of Celsius, one subtracts 32 degrees Fahrenheit, divides by 9 degrees Fahrenheit and multiplies by 5 degrees Celsius, and adds 0 degrees Celsius. Reversing this yields the formula for obtaining a quantity in units of Celsius from units of Fahrenheit. One could have started with the equivalence between 100 degrees Celsius and 212 degrees Fahrenheit, though this would yield the same formula at the end. C equals times 5/9. To convert C in Celsius to F in Fahrenheit, this formula may be used. F equals plus 32. Applications. Dimensional analysis is most often used in physics and chemistry and in the mathematics thereof, but finds some applications outside of those fields as well. Mathematics. A simple application of dimensional analysis to mathematics is in computing the form of the volume of an n-ball, or the area of its surface, the n-sphere. Being an n-dimensional figure, the volume scales as, while the surface area, being dimensional, scales as. Thus the volume of the n-ball in terms of the radius is for some constant. Determining the constant takes more involved mathematics, but the form can be deduced and checked by dimensional analysis alone. Finance, economics, and accounting. In finance, economics, and accounting, dimensional analysis is most commonly referred to in terms of the distinction between stocks and flows. More generally, dimensional analysis is used in interpreting various financial ratios, economics ratios, and accounting ratios. For example, the P/E ratio has dimensions of time, and can be interpreted as years of earnings to earn a price paid. In economics, debt-to-GDP ratio also has units of years. More surprisingly, bond duration also has units of years, which can be shown by dimensional analysis, but takes some financial intuition to understand. Velocity of money has units of years. How often a unit of currency circulates per year. Interest rates are often expressed as a percentage, but more properly percent per annum, which has dimensions of years. Fluid mechanics. Common dimensionless groups in fluid mechanics include Reynolds number, generally important in all types of fluid problems. Re equals rho Vd, mu. Froude number, modeling flow with a free surface. Fr equals V square root. Euler number, used in problems in which pressure is of interest. U equals V. History. The origins of dimensional analysis have been disputed by historians. The 19th-century French mathematician Joseph Fourier is generally credited with having made important contributions based on the idea that physical laws like F equals ma should be independent of the units employed to measure the physical variables. This led to the conclusion that meaningful laws must be homogeneous equations in their various units of measurement, a result which was eventually formalized in the Buckingham Pi theorem. However, the first application of dimensional analysis has been credited to the Italian scholar François David de Fontenec. It was published in 1761, 61 years before the publication of Fourier's work. James Clerk Maxwell played a major role in establishing modern use of dimensional analysis by distinguishing mass, length, and time as fundamental units, while referring to other units as derived. Although Maxwell defined length, time and mass to be the three fundamental units, he also noted that gravitational mass can be derived from length and time by assuming a form of Newton's law of universal gravitation in which the gravitational constant g is taken as unity, giving m equals L3t minus 2, by assuming a form of Coulomb's law in which Coulomb's constant k is taken as unity. Maxwell then determined that the dimensions of an electrostatic unit of charge were Q equals L3 halves m1, 2t minus 1, which, after substituting his m equals L3t minus 2 equation for mass, results in charge having the same dimensions as mass, viz. Q equals L3t minus 2. Dimensional analysis is also used to derive relationships between the physical quantities that are involved in a particular phenomenon that one wishes to understand and characterize. It was used for the first time in this way in 1872 by Lord Rayleigh, who was trying to understand why the sky is blue. Rayleigh first published the technique in his 1877 book The Theory of Sound.